So with these Lewis structure, we've been talking about how the electrons have been shared. So we draw the pair of electrons in between the two atoms because they are being shared. Covalent bonds, because they are sharing electrons, sometimes they don't share evenly. So often the two atoms do not share the electrons equally. That is, one of the atoms holds onto the electrons more tightly than the other. And when one of the atoms has those shared electrons closer, or they're holding them more tightly, we say that the bond is polarized, or we're basically making a polar bond. So a polar covalent bond is one in which the electrons are not shared equally. And this is very, very common. Most of the bonds that you will encounter in molecules are polar. If they are covalent, they're polar covalent. If they are sharing them equally, then we would call it a nonpolar covalent bond. Now, how do we determine if a bond is polar or nonpolar? How do we determine if two atoms are indeed sharing equally or not sharing equally? We look at electronegativity. So each element has an innate ability to attract electrons, and we call this electronegativity. So it's the ability of an atom to attract electrons in a chemical bond. One phrase that you'll often say or often hear is we might say that an atom is electron greedy. So something that is more electronegative, it's more electron greedy than one that is less electronegative. Now, for this electronegativity, it's essentially on a scale of 0 to 4.0, where fluorine is the most electronegative element. So fluorine has an electronegativity of 4, which is the highest, and then 0 is it's not electronegative at all. And I don't think any elements actually have an electronegativity of 0, but some of the metals on the left side, it gets pretty low. So here's an electronegativity chart. So like I was just saying, some of these metals over here, really low electronegativity values. Fluorine is the most electronegative atom on the periodic table. So it is the most electron greedy. So it has the strongest ability to attract electrons in a covalent bond. Generally for the trend, electronegativity increases as you go from left to right and bottom to top. So elements in the lower left are not very electronegative. Elements in the upper right are very electronegative. And this also kind of makes sense because you have your nonmetals in the upper right. Nonmetals like to gain electrons and become negatively charged. We call them anions, whereas metals like to lose electrons. So this kind of explains why when you put a metal and a nonmetal together, the metal ends up giving electrons over to the nonmetal because the nonmetal is more electronegative than the metal. So electronegativity differences is how we really determine if a bond is polar or how polar a bond is, whether it's like a little bit polar or very polar. So for example, hydrogen, and remember there's a scale going from 0 to 4, hydrogen is about 2.1, chlorine is 3.0. So which one is more electronegative? Chlorine had a higher number, so it is more electronegative. We would look at the difference in electronegativity, so the difference between the 2.1 and the 3.0. And when we subtract those two numbers, we get 0.9. Because we didn't get a 0 value, we would say that the HCl bond is polar. So for example, a polar covalent bond, maybe we just took a nitrogen. So here's my Lewis structure for nitrogen, which I just did as an example. Electronegativity for nitrogen is 3, so you have a 3.0. Electronegativity for the other nitrogen molecules is 3.0. 3 minus 3 is 0. The electronegativity difference between these two atoms is 0. Therefore, the electrons in the middle are being shared equally, and we would call this a nonpolar covalent bond. So anytime you have unequal sharing because there is a non-zero electronegativity difference, you're going to have a polar covalent bond. Now on this delta notation, which they started here, but I didn't really point to it, because the chlorine is more electronegative, it's going to be attracting the electrons a little bit more. So since chlorine's more electronegative, they're attracted to the chlorine atom, and they're basically being pulled away from the H. This gives the chlorine a slightly negative charge in that bond, and the H gets a slightly positive. So this delta notation, this is what this symbol here is. So delta positive and delta negative. That's basically saying that this chlorine here is slightly negative. It's not a whole negative charge like chlorine might be when it's an ion by itself. Like if we had sodium chloride, we have a sodium with a full positive charge and a chlorine with a full negative charge. So we're using delta for part of that. It's not a full negative, it's just a partial negative. And we put the partial negative here next to the chlorine, again, because chlorine was more electronegative. So we're basically saying this covalent bond between the hydrogen and the chlorine, it's a covalent bond. They're sharing electrons. However, they're not sharing equally because there is a difference in electronegativity values between hydrogen and chlorine. And the chlorine is a little bit more electrogreedy than the hydrogen. Therefore, the electrons that are in this bond are spending a little bit more of their time around the chlorine atom and less of their time around the hydrogen atom. Now we can assign this delta notation for pretty much any polar bond. So here we've got hydrogen fluoride. Here's the delta notation. It's basically saying because fluorine is more electronegative than hydrogen, we have the delta negative on the fluorine part of the bond. But all of these are polar covalent bonds. And also notice that the way these are drawn. So we talked about bond length. Notice that iodine, this is the nucleus of iodine, here's the nucleus of hydrogen. If we were to draw a straight line between the two nuclei and compare it to like hydrogen chloride, we're going to have a longer bond length over here. And that's generally true because iodine is a larger atom. So if you put larger atoms together, you're going to have longer bond lengths. I just like the fact that they've actually kind of drawn it to scale and it looks the way it really is. So hydrogen iodide, because iodine is larger, it has a longer bond length, and fluorine, being an extremely small atom, it has a much shorter bond length. So we talked about polar covalent. Nonpolar covalent is when they are sharing the electrons equally. So if you look at the two electronegativity values and they have the same value or even something that's extremely similar, so in organic chemistry, carbon-hydrogen bonds are often considered to be nonpolar. I think hydrogen is 2.1 and carbon is 2.4 if I remember correctly from the slide. But you end up getting a really, really small difference. And for the purposes of organic chemistry, we'll often say that this is a nonpolar bond. But for just learning, I would just go ahead and say that they would have to have the same electronegativity value for it to be actually classified as nonpolar. But basically what you end up having is the electrons are being shared equally between the two atoms. The bond is not polar, it's not polarized, and we call it a nonpolar covalent bond. And you're usually going to see that only when the two atoms are the same identity, so like two fluorines or two chlorines or two bromines. Here they say if it's less than 0.5, it's usually considered nonpolar, and that's generally true. Anytime you see two atoms of the same identity bonded together, so like all the diatomics, it's going to be nonpolar. So other examples would be like O2 or N2 or H2, or even in a larger molecule, like for example, C2H6. So I'm going to go ahead and draw C2H6. So this is a good chance to do Lewis structure review again. So carbon has 4 electrons, hydrogen has 1 electron. For carbon, there's 2 atoms, and for hydrogen, there's 6. So that means we're going to have 8 plus 6, so we're going to have 14 electrons total. And just kind of going to put the carbons in the middle and the hydrogens all around, connect everybody with lines, and then just take a quick check to see how many electrons we've drawn. So carbons in the middle, and I connected them all with lines. We've got 2, 4, 6, 8, 10, 12, 14 electrons. I was supposed to draw 14, so we're good. So now notice this bond right here in the middle, this is between a carbon and a carbon. So because this bond is between two elements of the same identity, we would classify that as a nonpolar covalent bond. Anytime you have a bond between two elements that are the same identity, it's going to be nonpolar. So to build upon the discussion of shapes of molecules, so like why do we even bother talking about Lewis structures? Is because once we know the Lewis structure, we can get some information on the shape of the molecule. And once we know about the shape of the molecule, we can make judgment calls on the intermolecular forces and the physical properties of these molecules. So how do we determine the shape of the molecule? Well, keep in mind that electrons and electron pairs, the electrons are negatively charged, and opposites attract. So positive is attracted to negative, and that also means a negative would be repelled from another negative charge. So the electron pairs surrounding an atom, they are going to repel each other. So electron pairs could just any pair of electrons, whether it's a lone pair that's not in a bond or two electrons that are in a bond. But this idea that electron pairs repel each other is called valence shell electron pair repulsion shear. Let me try that again. Valence shell electron pair repulsion theory, and we'll say VSEPR. So this acronym is pronounced VSEPR theory. So I'm going to use that from now on. But there's two types of geometries we're going to talk about as we talk about VSEPR theory. So electron pair geometry is the arrangement of bonding and non-bonding electrons. So bonding electrons pretty much means align. So let me draw our CO2 example. And I messed that up. So here is CO2, which we did as an example in the previous video. So a bonding pair of electrons would be something that's drawn as a line, or at least two dots in between atoms. Non-bonding electrons would be the lone pairs. So like these dots that I drew on the oxygen, those are non-bonding electron pairs because they're electrons that are on an atom, but they're not actually bonded to another atom. The electron pair geometry is basically focusing on the bonding and the non-bonding electron pairs, and the molecular shape is the arrangement of atoms around the central atom as a result of the electron repulsion. So we're going to go through a couple examples and talk about what we mean by these two. So a couple of different shapes. Tetrahedral is a shape that we'll get when we have four groups around the outside. So methane, we've got CH4. Those four groups are basically the four hydrogens. So you have your carbon here in the middle, and then 1, 2, 3, 4 hydrogens around that carbon. Now, if you consider the fact that molecules have access to a third dimension, whereas me on my PowerPoint slide, I only have access to the X and Y dimension, molecules have access to 3 dimensions. So if you try to take 4 bonding pairs and let them spread out in 3-dimensional space, they're actually going to take the shape of a tetrahedron, which is why we call the shape tetrahedral. And the bond angle that's between, so this bond that's going straight up and this one that's going off to the side, the bond angle that's between that, it's not 90 degrees, it's actually 109.5. So it's really important for you to remember these numbers, and we've got a chart to help you remember all the different bond angles. But tetrahedral is when you have 4 things around it, is the most important thing to remember from this slide. Now, if you've got 4 things around it, but one of those things happens to be a lone pair, then we're going to call it trigonal pyramidal. So this is ammonia. This is the common example for a trigonal pyramidal. It's got a nitrogen and 3 hydrogens, but then one of the things around the nitrogen is a lone pair, and I kind of just drew the lone pair as 2 dots, but in an orbital, so I drew a little circle to represent the electrons hiding or living in that orbital space. You've got 4 things around it, so it's still kind of forming a tetrahedron pattern, but given the fact that one of the 4 things is a lone pair, now we call the molecular shape trigonal pyramidal. And then bent is what we get when we have 2 lone pairs. So this is your water molecule, and we've still got 4 things total, but given that 2 of those things are lone pairs, we're going to call this shape bent. So bent meaning it's not linear, because if there was a linear molecule, it would look like this, but because we've got these lone pairs right here, it kind of squeezes these 2 hydrogens closer to each other, and we end up getting this bent shape going from hydrogen to oxygen to hydrogen again. So that's what we call bent. It's still got like 4 total groups, but 2 of them are lone pairs called non-bonding, and 2 of them are bonds, so they're bonding, and that's why we get the bent shape. Linear, So I used CO2 before, but CO2 is also a classic example of a linear molecule. So linear, as in it's just forming a straight line. Now the reason why this one forms a straight line is because we don't have lone pairs around that central atom. So we actually don't have that here. So in the water molecule, we did have 2 lone pairs, but in the CO2 molecule, we don't have the lone pairs. So you're not going to have repulsion between this non-existent lone pair and this atom, but we still have repulsion between the 2 atoms, because these 2 atoms, these 2 oxygens, they still have electrons on the 2 sides. And part of VSEPR theory is the electron pairs are going to repel each other, and they're going to try and get as far away apart from each other as possible, which means they end up going to 2 complete opposite sides. So essentially, the bond angle between here is 180 degrees, because that's as far as apart they can possibly get. If they both go in 2 opposite directions, they're as far apart as possible, and you have 180 degrees between them. So we're going to call that linear. And then another one is called trigonal planar. So trigonal planar results when you've got 3 things. So linear was essentially 2 things. So you have the carbon. Around the carbon, there's just 2 things. You just have an oxygen over here and an oxygen over here. If you've got 3 things around it, so in this example, this CH2O formaldehyde, you've got a hydrogen, and an oxygen. That's 3 things. If they were to spread out as far apart as possible, then you end up with this triangle shape. So if we were to connect these, it just makes a simple triangle. That's why it's called trigonal. And then they actually will be in the same plane. So if I could turn this molecule on its side, all 3 of them could lie flat on the paper or flat on a table, which is why we call it planar, trigonal planar. And then the bond angle between these is 120 degrees, because that's just what results when the 3 groups spread out and get as far away from each other as possible. So this is a summary. So over here is important to pay attention to bonding and non-bonding electron pairs. So bonding basically means a line or a bond, and then non-bonding is a lone pair of electrons. So anytime you have 2 dots. The electron pair geometry just considers all of them. So notice that with all of these, and actually there is a typo, so like this one should say 2, and this one should say 3. But notice that with these 3, the 2 numbers, 4 plus 0, 3 plus 1, 2 plus 2, those all add up to 4. So the electron pair geometry for all 3 of those is tetrahedral, because it's all 4 things total when you consider bonding and non-bonding together. But then molecular shape is when we consider, okay, how many of them are lone pairs? So if none of them are lone pairs, it's still called tetrahedral. If one of them is a lone pair, then we call it trigonal pyramidal, so that's like the ammonia molecule. And if 2 of them are lone pairs, then we call it bent, and our example was the water molecule. So you'll want to try and memorize these. I suggest flashcards. So electron pair geometry, molecular geometry, bond angle, and then drawing some examples. So draw the Lewis structures for these examples. And then you can Google VSEPR theory, and you can see more colorful pictures. I would suggest doing that, especially if you take an example molecule, draw the Lewis structure for it, and then try to take a guess on what the shapes would be, and then Google it, where if you type in the molecule and then like Lewis and then VSEPR, you could see some 3-dimensional molecules or models of these molecules. So then if you have nonpolar molecules with polar bonds, it's the same kind of thing. I mean, we're still talking about VSEPR theory in the same sense, so nothing's really changing there. However, you can have a molecule with polar bonds, so the electrons are being shared unevenly between the 2 atoms, but then the overall molecule ends up being nonpolar. So CCl4 is just one example. It has polar bonds, so just looking at a carbon-chlorine bond, we're going to have an electronegativity difference between carbon and chlorine. So this is a polar bond, but given that we have 4 CCl bonds in the carbon, around this carbon, they're basically going to cancel each other out. So all of these, we can apply the delta notation and have a partial positive for the carbon and a partial negative for the chlorine, because chlorine's more electronegative. But the interesting thing is that when you have 4 polar bonds that are spaced out like this in the form of a tetrahedron, they actually end up canceling out perfectly. So it's kind of like if you were to think of just 2 items, like if you were to balance something in your hands, like think of like a meter stick or something. If you found the middle of that meter stick doesn't fall out of your hands because it's kind of balanced on both sides. It's this sense of balance or symmetry that we want to think about. So in 3-dimensional space, if you've got 4 that are all in terms of the polarity, in terms of if you've got 4 bonds in terms of polarity that are equal magnitude, is what I'm trying to get at, then they'll kind of balance each other out, and then you end up with a molecule that's nonpolar overall. So this works with tetrahedral, where all 4 things are the same. So here it's 4 carbon chlorines, but it can also work with trigonal, planar, and linear. So for the trigonal planar example, we might say BH3. So a Lewis structure for BH3 might look like this. Now we've got 3 polar bonds, so between an H and a boron, probably not going to have an electronegativity difference of 0. So this is a polar bond right here, but we've got 3 that are of equal magnitude. And if you have a trigonal planar geometry, you can also have all 3 canceling each other out perfectly, and you end up with a nonpolar molecule. So it's important to understand we're talking about the bonds being polar, but then the molecule overall being nonpolar. And then this can also happen with linear. So I'll use CO2 again. Here's our Lewis structure for CO2. We've got a polar covalent bond here and a polar covalent bond here, but because these 2 polar covalent bonds are of equal magnitude, so they're both equally polar. This one we've got a delta negative and a delta negative on the 2 oxygens with a delta positive on the carbon. Because they're of equal strength, it's perfectly balanced, and this is more like a seesaw or the meter stick in your hand. The whole molecule ends up being nonpolar overall. So we have polar covalent bonds, but a nonpolar molecule overall.